What happens in the wintertime when it snows? Is the weight that's being applied to this going to change? It absolutely is. What if we get a 100-year storm event from a wind standpoint? We're going to get an increase in load, okay? So all of these numbers will be applied with a factor of safety, okay? We won't go a whole lot into factor of safety, but typically your structural engineers are going to use a factor of safety of about 1.5 to 3. Okay, so what we would actually do when we come down to selecting this bolt is if we know that we determine that 11,318 is the maximum load capacity it's going to experience in shear, we're going to design it for 19,000 to 35,000 PSI. Okay, does that make sense? And I don't say that to confuse you, I just say that to give frame of reference for Christian's question on, well, is 11,317 or is 11,318 correct? Well, once we run it through the factor of safety, that washes all out, okay? So for the purpose of these assignments, yes, I guess 11,318 is the most correct, but I'm not going to take points off for you for 11,317, okay? Does that make sense to everybody? All right. So then, if we wanted to look at, well, instead of doing one bolt, we need to do 4 bolts for whatever, configuration, etc., things like that. Then you just determine and just say, well, if one of them needs to pick up 11,318, if there's 4 of them, each one needs to pick up 11,318 divided by 4. Okay? So that's how those bolted connections go into place. And typically, we're going to go to a system like this just because that has the potential to give you redundancy in the event that you do have an error with one of your bolts. If you only put one bolt in there and that thing has a problem, now you no longer have a structure, right? But if you got 4 bolts in there with your factor of safety, if you have an issue with one, you still have an erect structure, okay? So that's why we'll see we're probably not typically dropping 1 bolt into a steel member, okay? But for the purposes of our calculations, it makes it easier, okay? Questions on these types of problems? I'll give you the chance over the weekend to do the reading of this. Tuesday we'll come back and we'll run through these problems again. We'll use different numbers and we'll set things up before I give you the next assignment as well. Okay? But that's direct shear. The other concept that we address in chapter 3 is shear in a beam. Okay, and so you can think of back to chapter 1, right? We did our force resolutions, and then we did analysis on simple beams, right? Where we have to determine what's going on with the different forces. Okay, so we're going to do the same thing with shear, and then when we get done with shear, we'll look at bending. And then once we're done with shear and bending, I think that we've got enough of the basic understandings of principles where we can start looking at specific material types and how we size them, okay? So let's take a peek. Let's say that one's 400 pounds. That one's 300 pounds. What does that thing look like? 10 foot? So that's 3 foot, that's 3 foot, so that's 4 foot, terrible T. Okay, so we still have to go through the initial analysis that we did in our simple beams. So we have to check and make sure that we have static equilibrium. Okay, so the sum of all our forces in the x direction have to equal 0. The sum of all the forces in the y direction have to equal 0, and all our rotations have to equal 0. Okay? I'm also going to say that any force in this direction, in this x direction is positive, forces in this y direction are positive, and rotation in this direction is positive. Okay? So, anything operating in the x direction? We don't, right? That's the great thing about these simple beams. We don't take any wind into account, we don't take friction, there's nothing driving across these things, nothing moving on, so we're good there. What about in the y direction? We have some things that we have to take account of, right? What do we need to take into account?
3 pounds going down.
Yep, so we have a negative 300 pounds. A negative 400 pounds. What else?
R1.
And then R1 and R2, right? So, we know R1 and R2 have to equal 700 pounds. Right? Does everybody agree with me on that? Okay? How do you want to determine R1 or R2? Do you want to do analysis about R1? Do you want to do analysis about R2?
Do R1.
Do about R1? Okay? So our moment about R1 has to equal 0. Okay, so what's tending to cause rotation about R1? Does R1 cause rotation? Why not?
Because it's no distance away.
It's traveling through that point, right? Remember that our moment is a force times a distance. Because R1 travels through R1, it has a distance of 0 feet. Okay, so it doesn't cause any rotation. What about 300 pounds?
3 feet away.
300 pounds is 3 feet away. How's it trying to spin the thing?
Positively.
It's trying to spin it positively the way that we've defined it, right? If you defined that this is positive, okay, you're just going to have flipped signs in everything that you do. All the numbers come out the same at the end, okay? So 300 pounds times 3 feet. What else do we have?
Times 7 feet.
400 pounds times 7 feet. Good. So everyone saw what Hunter did here? Told us that this 400 pounds was 7 feet away. A couple people got caught up. I made comments. When you put into the moment equation, you just use this distance. Okay? So you have to make sure when you're setting up this equation, whatever force you're applying it to, you have to measure the distance from where the force is being applied to the reaction that you're analyzing, okay? And that's not unique. Everybody does it. I did it when I took this class a dozen and a half years ago. I've seen it every semester I've taught it, okay? So just work on breaking yourself of that habit. Okay, so 900 pound foot, 2,800 pound foot, minus 10R2 pound foot. So all that has to equal 0. Okay? So 3,700, right? So R2 is 370 pounds. Anyone take any grave issue with that statement? Does that seem agreeable? Good with it? Okay. What does that mean for R1?
330 pounds.
330 pounds. Does that make sense physically when we look at the beam? Should R2 be picking up a little bit more load than R1? Makes sense, right? There's a larger load that's the same distance away. Okay? So, this isn't new to us. This we've done. Okay? What's going to be new to us is now we're going to march across this beam and figure out what's happening as these forces are trying to shear the beam into two pieces. Okay? And we're going to make a diagram that shows what's happening with that. All right? We're at here, 1025. Okay. So, kind of run out of space, I guess. But I guess we could. So we'll redraw our beam, and we're going to call it our shear diagram. Okay, so at this point we are at R1, and over here we're at R2. Okay? And so what we can think of is we're going to consider the beam to the left of wherever we're referencing. Okay, so if I tell you that we're 1 foot away, don't think about the 300 pounds, don't think about the 400 pounds, don't think about R2, because the beam doesn't know about those things yet. Okay, it only knows what's occurring to the left of it. Okay, so if we start out 1 foot away from the beam, what's trying to shear it? What's trying to rip it in two?
Nothing.
R1, right? Think if, okay, so if my finger and thumb are R1 and I grab on here, if I pull on this, can I tear the paper? I certainly can, right? Okay, so we can have shear originating anywhere on the beam. Okay? So, if we're 1 foot away, the only thing that's going to be operating in shear, again, and we're traveling left to right, the only thing operating in shear is going to be R1. Okay? And it'd be the same as we try and get closer and closer to R1. Okay, let's move 6 inches away. Still only R1. Move 3 inches away. Still only R1. 1.5 inches, 3/4 of an inch, 3/8 of an inch, 3/16 of an inch. Okay? As we continue moving closer and closer and closer, it's still only R1. So, what you will do on your shear diagram is we'll again define which way is going to be positive. We'll say that up is positive. It's just, that's what makes the most sense to me. Okay? Your shear from 0 to 3 feet is going to be equal to the magnitude of R1. Okay? So 330 pounds. Let's see. So that's 10. So I'm going to go to about there. Now, what happens when we get just on that side of our 300-pound force? What does that 300-pound force try to do to our beam? We're just talking about shear. Now it's trying to pull down on the thing, right? With how many pounds is it using? 300 pounds, okay? So we immediately drop down 300 pounds, okay? Because remember, you still have R1 trying to shear the beam as well, okay? R1 is going to be trying to shear this beam the entire way as we're going along with 300 pounds. Now, this point load is going to be trying to shear this thing with 300 pounds all the rest of the way across, okay? So what happens when we get to 7 feet? We get an additional 400 pounds in shear pushing down on the beam, okay? What does that number look like? What other force do we have that's 370?
100th one.